Hello physics students, this is Dr. Brenzy and this is lesson 5.2.5, and in this lesson we are going to be able to apply work, energy, and power to solve problems involving rotational motion. In Unit 3 we learned that work is a force applied over a distance, so that is something that's really important to remind ourselves about, is that whenever we have a force pushing on a box and we push on that box over a distance, we can say that the work we did is the force times that distance. And if you remember, we have to make sure that our force is parallel to the displacement of our object. So if you're on a flat surface, you're pushing a box, the force has to be parallel to the direction you're pushing it in order for that force to do work. And if it's not exactly parallel, then we have to take the component of the force in that direction to figure out what the work is. And this fact that the force has to be parallel to displacement is the reason why centripetal force, that is the force that is pointing toward the center, does no work, because it is actually perpendicular to the displacement of our object. Another important thing that we need to recall from Unit 3 is that the work done on an object is going to change that object's kinetic energy, and we call that the work kinetic energy theorem. So it's simply written as the work done is equal to the change in kinetic energy. So if you put work into a system, you do positive work, the kinetic energy will increase. If you do negative work on a system, then it will remove kinetic energy. And then we learned that the power is the rate at which work is done. So power is equal to the work done divided by the time in which that work was done. So those are some important concepts that we learned from Unit 3. If you remember back from Unit 3, you remember that we had a formula for kinetic energy. So kinetic energy equals 1/2 mv squared. Now in rotational motion, we have something very similar. We can write kinetic energy equals 1/2. We're going to replace the m with its version of rotational motion, which is the moment of inertia, I. And then we're going to replace the velocity v with omega. So we have, for rotational motion, Ke equals 1/2 times the moment of inertia times the angular speed squared. Now, this next point that I'm going to make is more directed towards AP students, but those of you in advanced class, I think you can follow along, but it does involve some algebra. So let's actually prove that this really is the correct formula, at least for a point that is going around a circle. So I drew a circle here. I have a point on that circle, and it has a linear velocity around the circle of v. So its kinetic energy, oops, one of the other things I forgot to tell you is that this radius is r, and the angular speed of our loop, or the angular speed of our point around its circle is omega. So we can write, we definitely know that kinetic energy equals 1/2 times mass times velocity squared. So we can think of this as having a kinetic energy along a line equal to 1/2 mv squared. And I'm actually going to show you that by rearranging some terms a little bit here, we're actually going to come to this equation right here, Ke equals 1/2 I omega. Well, we know that the velocity, the linear velocity at this point is equal to omega times r. So let's replace v squared with omega times r. And we have to square both of those terms, so let's put that in parentheses. Well, let's go ahead and square those terms. So we have 1/2 m times omega squared times r squared. Then I'm going to rearrange these terms because with multiplication, order doesn't matter. So let's write this as 1/2 m times r squared times omega squared. And this thing that I just underlined right here happens to be the moment of inertia for a point mass that is going around in a circle at radius r. So I can rewrite this as 1/2 times I times omega squared. And that's the formula that we get over here on the right. So at least for rotational motion, or of a point mass, we can actually show that its rotational energy really is 1/2 times I omega squared. And it turns out that is true for all rotating objects, no matter what their moment of inertia is. Okay, well, let's do a really quick example. Let's say I have a tire, and it has a radius of 0.4 meters. It is spinning at an angular speed of 2 radians per second, and it has a mass of, let's say, 0.8 kilograms. It's a pretty light tire, but I'm just doing this for an example. So let's apply our kinetic energy formula. Oops. Forgot to say that one of the things in that kinetic energy formula is the moment of inertia, and it turns out the moment of inertia for a loop is m, its mass times its radius squared. So if I were to calculate m times r squared, I would find that I get a moment of inertia equal to 0.128 kilogram meter squared. Now that we know the moment of inertia, let's go ahead and plug that into our rotational kinetic energy formula, 1/2 I omega squared. So 1/2 times I, which we just found out, 0.128, times omega squared, which is 2 squared, and it turns out when you punch all this into your calculator, you get 0.256 joules. All right. So that's how you calculate the rotational kinetic energy of a tire or any other object that has a moment of inertia. Right. Now, those of you who are in AP, we're going to finish up with these notes. And those of you who are in advanced, you are technically finished, so if you want to drop off at this point, you can, but I don't think that this concept is too difficult for you. It's just that we won't be practicing too many problems that apply this. So there are times when you can actually have both linear and rotational kinetic energy. So let's consider a cylinder that is rolling along a table. This cylinder has some sort of velocity v. It's actually called v naught here in this diagram. So this cylinder is actually moving toward the left. Its center of mass, which is right in the middle, is moving toward the left at a velocity v naught. And it also is spinning around as it does that. And the total kinetic energy of this system, of this rolling cylinder, is 1/2 times its mass times its velocity squared, plus 1/2 times its moment of inertia times omega squared. 1/2 mv squared, that is what we call its translational kinetic energy. And translational is a fancy word for along a line or linear. And its rotational kinetic energy is 1/2 I omega squared. And if we really wanted to, we could actually play around. We could actually figure out what I has to be. I think for a cylinder that's solid, it turns out to be 1/2 1/2 mr squared. So we could actually come up with a formula for what its total kinetic energy is. But for now, I just want you to understand that there is a possibility that you can have both linear and rotational kinetic energy. And there are going to be situations like when a ball, or not a, well, when a ball or a cylinder or a hollow cylinder is actually rolling down a ramp or rolling along some surface. It's going to have both translational kinetic energy and rotational kinetic energy. And we're going to actually find out some really interesting consequences of having both rotational and translational kinetic energy. Alright, we're going to practice applying these concepts tomorrow in class, and I look forward to seeing you then. Bye.